So, good evening, everyone. I'll start today's class. Am I audible? Can someone confirm?
Yes, sir.
Okay. So, I'll start today's class. First, I'll give a quick recap of what we discussed in the last class, and then I'll quickly move to today's topics. So, last class we were talking about interpolation, right? So before that, we had talked about what is called as regression and how to find the best line of regression from a set of data, how to fit a straight line to any set of random data which is given to us. And then we move to interpolation. I described the main difference between regression and interpolation. So here you can see two figures on your screen. The first one is called the line of best fit, and the second one is called the interpolating curve. So suppose you have performed a experiment and you have a set of data with you. So that data might be random, right? So it will not fit in a straight line. So in regression, what we do is we find the straight line which is closest to all the points. That is the error, or the error which is error between the experimental data and that predicted by a straight line is minimum. That straight line we consider as the straight line of best fit. And your best line of best fit, it necessarily doesn't pass through all the points. It is the closest, it is a line which passes closest to all the data points. Whereas in interpolating curve, we have a set of the same set of experimental data. And if we want to find out what is the interpolating curve, uh, that is basically a curve which passes exactly through all the data points, and it traces all the data points in that curve. And that curve is basically called the interpolating curve. So this is the basic difference between regression and interpolation. So then we saw what is the difference between interpolation and extrapolation. In interpolation, suppose we have a set of data, say x1 to xn, and we have our the experimental values or the values of the dependent variable within that range. Say for x1 we have an experimental value of y1. Similarly for x2 we have a value of y2. And as we move forward till xn, you have a value of yn. So we basically plot all these points on the xy plane, and we connect them using a curve, a random curve that is called the interpolating curve. So if you want to find any value of y for a particular value of x within this range, then your curve is valid. That is, this interpolating curve is only valid for the range of x1 to xn. Any value of x you give within this range, you will get the value of y from the interpolating curve. However, outside this range, outside the range of x1 to xn, if you have a particular value of xn, your curve doesn't give you the value of yn. So this curve is only valid between x1 to xn, not outside the range, either greater than xn, or if you give any value less than x1, your curve is not responsible for giving you that particular value of y. So as I told, that this curve is valid only within this range of independent variables, that is x1 to xn, and there is no information of the curve outside this particular range. Similarly, in extrapolation, what we do is we plot all the data points, the experimental data points from x1 to xn and their corresponding y values. However, if we want to find out the value of a point, that is say xn plus 2, at xn plus 2, what will be my value of y? So we basically extend that curve, and we find out what is the value of xn plus 2, what is the value of y at xn plus 2. So this is known as extrapolation. So your extrapolating curve is valid throughout the range, that is from minus infinity to infinity. So there our extrapolating curve is valid. Hmm. So now we go deep into interpolation. We have different interpolating curves, or fitting a polynomial of degree n to a set of n plus 1 data points. We have different interpolating polynomials. The most famous of them is the Newton's interpolating polynomial. In that we have the values of y for equispaced value at different equispaced values of x. For x1 we have y1, for x2 we have y2. Like that we move forward. So there, if we are asked to find the value of we are asked to find the value of the interpolating polynomial, what we do is we take the help of what is called as forward difference. So forward difference is represented by delta, right? Any kind of difference is not represented by delta. So this delta yi is given by yi plus 1 minus yi. And similarly, delta xi is given by xi plus 1 minus xi. So it is the difference between two consecutive values of of the variable. So this is called the first order forward difference. If we want to find out what is the second higher order forward difference, second order, third order. So what we do is it is represented by the second order forward difference is represented by del square of yi. So del square of yi is given by del yi. Again we can replace del yi by yi plus 1 minus yi. Then if we open the bracket and we do the simplification, we come to a value. If we simplify it, we get del square of y naught, or del square of yi is yi plus 2 minus 2yi plus 1 plus yi. So if we just substitute I equal to 0, that is for the first value, del square y naught will be y2 minus 2y1 plus y naught. So like this, we can find out the higher order forward differences for any variable for y1, y0, y2, anything we can find out. So the general formula for higher order differences, del j of yi, that is the jth order forward difference, is given by del j minus 1 yi plus 1 minus del j minus 1 yi. So this is a generalized formula for the higher order forward differences. So now, once we get the forward difference, how to move forward? So our goal is to basically find the interpolating polynomial, right? So here the interpolating, in order to get to the interpolating polynomial, we do a simple variable transformation so that our calculation becomes simpler. So we know that del xi is xi plus 1 minus xi, right? We take a variable alpha, which is given by x minus x naught by delta x. So your x can be replaced by x naught plus alpha delta x. X naught is the first value of x. So your interpolating polynomial, it can be represented in this form: a naught plus a1 into x1 x minus x naught plus a2 into x minus x naught into x minus x1. In this pattern we continue. And this our goal will be here to find out these coefficients a naught, a1, a2, a3 up to an for the set of data which is given to you. So if we just substitute, we know at the value x equal to x naught, your polynomial should be equal to y naught. Similarly, at x equals to x1, your polynomial must be equals to y1. So like this, we can go on substituting. So if you substitute x equals to x naught here, only the first term will remain. All other remaining terms will go to 0. So basically, you can write a naught, that is the first coefficient, that is equals to y naught. Similarly, if we substitute x equal to x1, we will get y1, that is Pn of x is y1, equals to a naught plus a1 into x minus x naught. Only the first two terms will remain, remaining all other terms will cancel and go to 0. Similarly, for that, thus we can get a1 will be equal to y1 minus y naught by x1 minus x naught. So y1 minus y naught is again del y naught, and x1 minus x naught is del x naught. So we can find out the values of a naught and a1 like this. Similarly, if we go on substituting x equals to x2, your polynomial value is y2. If we just substitute this and do some calculation simplifications, we can find out a2, which is del square y naught upon 2 del x square. And a1 was del y naught by del x, and a naught was y naught. So if you have further a3, a4 like that, we have a generalized formula for that, which is an equals to del n of y naught, that is the nth order for forward difference of y naught upon n factorial multiplied by del of x power n. Correct. I hope this is clear to you. Is it clear? Any doubts? Any doubts, anyone?
No, sir.
Okay, fine. So now we have got the values of a0, a1, a2 up to an. All the coefficients values we know, right? So now our job is to substitute this and find the polynomial. So to do that, what we do is we do again a simple simplification as we did with the variable transformation there. So your alpha we had taken as x minus x naught by delta x, right? So our this is our alpha. X minus x naught by del x equals to alpha. Similarly, if we substitute this x minus x1 by delta x, if we try to represent it in terms of alpha, what we can write is, if we just substitute x1 is, what is x1? X1 is x naught, the previous value, plus the discretization, right? Delta x. X minus within bracket x naught plus del x by del x. If we simplify this, we'll get alpha minus 1. Similarly, if we generalize this, we'll get x minus xk by delta x will be equals to alpha minus k. So here this was this Pn of x. This is my interpolating polynomial, right? Y naught plus del y naught by del x, all these terms are there. So here if we just simplify it and write in terms of alpha, what we can write is y naught plus this thing x minus x naught by del x is alpha, right? Again, x minus x naught upon del x is alpha. This one is alpha. And this term is x minus x1 by del x is alpha minus 1. So we have written alpha into alpha minus 1 into del square y naught by 2 factorial. Similarly, we can substitute this and we can get a simplified formula in terms of alpha. So the final Newton's interpolation formula looks like this. Pn of alpha is y naught plus alpha del y naught plus alpha into alpha minus 1 into del square y naught by 2 factorial up to nth term alpha into alpha minus 1 alpha minus 2. This multiplication will go on till alpha minus n minus 1 multiplied by del power n y naught by n factorial. So this is the final formula or the final version of the Newton's interpolation formula. So as you saw here, it is a very hectic approach, right? It is a time consuming and a computationally very expensive approach. So how to write the code for this, you might think, how to do it using the MATLAB. So when you want to write anything in MATLAB, you need to have a concise or a generalized approach for this. So what we do here, we have a matrix approach for this. How to find out these coefficients if you don't want to, similar to the regression approach, in linear regression also, we had a matrix approach. We formed the matrices and then we manipulated them and we could find the coefficients, right? So in matrix approach, what we do is we write all the equations and then form the matrix. So you have your, suppose you have 4 data points, x1, y1, x1, y1, x2, y2, x3, y3, x4, y4. We have 4 data points, right? So y will be given by a0 plus a1x plus a2x square plus a3x cubed. Similarly, y1 will be a0 plus a1x1. Like this, we will have y1, y2, y3, y4. So 4 equations are there. So these 4 equations we can write in the form of a matrix, right? If we write this like this, y1, y2, y3, y4, and this is my x matrix, 1, x1, x1 square, x1 cube. Similarly for x2, x3, and x4, and we have the RHS matrix, which is a0, a1, a2, a3. So here my aim is to find out this matrix, right? The A matrix. This is my A matrix or the coefficient matrix. My A matrix or coefficient matrix. So y is given by x into A. That is A is equal to x inverse y. If we can find out the inverse of x and then multiply it with y, so here we can directly find out the coefficients. We don't need to remember any kind of formula. So once you get this matrices, that is the coefficients, we can directly substitute in our this polynomial and find out the final answer. So the thing here is using matrix, we need a matrix approach because we want to break it down. That is, we have a mathematical approach, and if we want to code it or if we want to automate it, that is write MATLAB programming, then that's we need a matrix approach, which makes it much more concise and generalized to write the MATLAB code. I hope this is clear to you. This is what we had discussed in the last class only. Then we had solved some examples and we found out what are the interpolating polynomials. And then we talked about another polynomial, interpolating polynomial, which is Lagrange polynomial. Similar to Newton's interpolating formula, there is another approach or another way of finding out an interpolating polynomial. So here you have the Lagrange multipliers, the formulas for that. You can just go through it. And if you have any confusions, we can talk in the next class. So I had already discussed in the last class. I solved a problem using this Lagrange approach also. So writing the MATLAB code, I didn't do it because it was very simple. If you have any, you can take up an example and you can write the MATLAB code for this Lagrange or the Newton's interpolating polynomial also. It's very simple. We can write it in 2-3 lines. Then we saw what is Newton's divided difference. So there are three kinds of interpolating polynomial. The first one was the Newton's interpolating polynomial. Second was Lagrange's polynomial, and now we have the divided difference thing. So again, the divided difference thing is nothing but another approach of finding the differences and then informing the final interpolating polynomial. So here again we have say four sets of data x1, y1, x2, y2, x3, y3, and x4, y4. We find the first order divided difference, which is given by y21, then y32, y43. This is the first order difference. Second order difference is between y21 and y32. We find out what is y321 and y432 between 43 and 32. Similarly, the third order difference we find out. All these things we find out, and then we substitute here the final interpolating polynomial, which is f of x, which is given by y1 plus x minus x1 into y of 2 comma 1, the divided difference x minus x1, x minus x2, y321, x minus plus x minus x1, x minus x2, x minus x3 into y4321. We have the divided difference interpolating polynomial also. We can find it out like this. Just 1 second. Okay, so this was all about the interpolation. So now once we have this interpolating polynomial, we go to the next module, which is called as numerical differentiation. So now we talk about what is called as numerical differentiation. That is our 8th week topic. So here we will see when we use numerical differentiation, what are the different techniques of numerical differentiation. So we have learned, every one of us has learned calculus in our +2, right? So there we have seen that we have a generalized analytical expression for finding the differentiation of the derivatives of different functions. So then why we need numerical differentiation? So first we need to understand why we are studying this topic. So the question is, why numerical differentiation is necessary? So the first answer is yes, we have the analytical expression for differentiation of different functions, but always we cannot find out the derivative of any random function. We don't have the analytical expressions for the differentiation of every mathematical function. And also you can have combination of multiple functions, and then it might be difficult to find out the analytical expression or do the chain rule and differentiate again and again. That might be computationally expensive, right? So the analytical expression of the function, that the differentiation of that differentiation might be difficult. Just for 1 minute, I'll come back. Just a minute. So, yes, as I was telling, the analytical expression of the function, the differentiation might be computationally expensive. So that's why we use the technique of numerical differentiation to find out the derivative of the function at any particular point. So here, unlike analytical differentiation, where we get an expression of the derivative of a function, here we directly cannot get the expression, or rather we can find out the differentiation of a function directly at a particular point. So what I'm trying to tell is, in analytical differentiation, suppose what you do is you are given a function, say some function is there, ax power n, and you are asked to find the derivative of the function at say x equals to 0.5. So if you are asked this, what we do is, using the normal procedure, we find out what is f dash of x, we get an analytical expression for that. Then we substitute, in place of x, we substitute x equals to 0.5, and then we find out f dash of 0.5. So here, this expression is readily available with us, right? So this analytical differentiation expression, but in numerical differentiation, we don't have a direct expression for the particular differentiation. We use different forward differences or backward differences to find out the exact value of the derivative of that function at a particular point. Okay, so now we need to understand about numerical differentiation, right? So So in numerical differentiation, we use the concept of finite differences. The finite differences formula for numerical differentiation. So like when we want to find the first order difference, the first order derivative of a particular function, say dy by dx, if we want to find out, what is the meaning of this? It is the small change in y, the ratio of small change in y for a small change in x. So we can represent it as del y by del x, right? So using the normal concept of forward difference, we can write this as y2 minus y1 upon x2 minus x1. So this is the generalized thinking behind finding the derivative of a function. So what we do here is we approximate the derivative at a point Say we want it at x equal to 0.5. We find out the value of the function at x equal to 0.6 and then subtract it from x equal to 0.6 minus x equal to 0.5 upon 0.6 minus 0.5. I'll show you how we do that. So we approximate the derivative at a point by using the values of the function at the neighboring points. So in order to approximate this functional values at different point, we use the Taylor series expansion. So now the question arises how we do that. That is normally, suppose I'll show you geometrically first. Suppose we have a function like this. Say we have a function like this, and you want to find out the value of the derivative at this particular point. Say at xi, I want my value. So what we do is we divide this function into different discrete points, right? First of all, this is one value, this is one value. From a continuous curve, we just divide it into different discrete points, different equispaced points, we divide it. So then what we do is we find the values of the function at the two neighboring points. So at xi we want the derivative, we find the value at xi minus 1 and xi plus 1. Then we find out what are the functional values at those points. This is the functional, 1 second. So one value. So this is my fxi plus 1. Top one is fxi and this one is fxi minus 1. So once we have this, we can find out what are the, using the Taylor series approximation, we can find out these values and then we can find out the derivative of this function. So we'll see here now. First, we'll look into the 2-point backward difference formula. So if we want backward difference, suppose at xi I want my derivative, we go one step backward. That is that we go at xi minus 1. So we have to basically find out the value of fxi minus 1 using Taylor series. So here your h is xi minus 1. So now if you want to write down xi minus 1, how can you write down? So it is basically f of xi minus h into f dash xi plus h square by 2 factorial f double dash xi minus h cubed by 3 factorial f triple dash of xi, and we continue like this. So what we do is we only consider the first two terms, right? Retaining, because as the power of h increases and h is very small here, the further terms it reduces. Retaining only up to second order terms, what we get is f of xi minus 1 will be equal to f of xi minus h f dash xi plus h square by 2 factorial f double dash of xi. So this term here, this h square by 2 factorial f double dash xi, this is basically the truncation error. Truncation error, and its order is of the order of O of h square, right? Since there is h square term here, we call the truncation error here is of the order of O of h square. So if we simplify this one, we can find out f of xi minus 1 will be equal to fxi minus hf dash xi plus O of h square. From this, if we try to find out what is f dash of xi, so this is f of xi minus f of xi minus 1 upon h. So this is the final expression for finding out the backward difference. This is the final expression for find out the derivative of a function using backward difference formula. We call it BDF. And your error here is of the order of O of h square. So is this clear? Any doubts, anyone?
Clear, sir.
Anyone? Any other questions?
Okay.
Okay. Okay, fine. Just okay. So this was using the backward difference formula. So now if you want it using the forward difference, so how do you proceed? So we have what is called the 2-point forward difference formula. So we can write f of xi plus 1. So it is one step forward, right? So we write f of xi plus hf dash xi plus h square by 2 factorial f double dash xi plus h cube by 3 factorial f triple dash xi plus like this it continues, right? So again we consider up to the second order term and we write it equals to fxi h f dash xi h square by 2 factorial. So basically this term h square by 2 factorial f double dash xi, we write it as the error again, right? We write it as O of h square. If you want to find out f dash xi from here, it is basically f of xi plus 1 minus f of xi on h. So here one thing I missed it. So here, if you when we are finding out f dash xi here, so here is the h term is there, right? H into f dash xi. So when we divide throughout by h, our error will also get divided by h. So your error will no longer be of the order of O of h square, rather it will be of the order of O of h, right? So we have the error here, which is O of h here. Similarly, here also this O of h square is this one. So if we divide by h throughout, this will be of the order of O of h. So this is the formula. This is the formula for forward difference. So we basically have three schemes. One is the forward difference, the backward difference, and the central difference. So now we will see into what is the central difference. 2 point So in 2 point central difference, so backward difference, we go one step backward. From xi, we go one step backward, which is xi minus 1. So your formula will only involve xi and xi minus 1. Again, in forward difference, we go one step ahead or one step forward. So our formula involves xi and xi plus 1. Similarly, in 2 point central difference, it will, your xi is here, one step backward is xi minus 1 and one step forward is xi plus 1. So your central difference is your this derivative point will stay at the center and only the two extreme points will take part. One is xi plus 1, other is xi minus 1. So here your formula will involve xi plus 1 and xi minus 1. So for that, what we do is we write both f of xi plus 1 and xi minus 1. So what is fxi plus 1? From the previous thing, we can write like this, right? H f dash xi plus, just up to second term we'll write. And if we write fxi minus 1, it is f of xi minus hf dash xi. So this is my first equation, this is my second equation. From this, we have to find out xi f dash xi. So what we do is we do equation 1 minus equation 2. So if we do this, we can see it will be fxi plus 1, f of xi minus 1. So fxi will cancel. This will be 2h f dash xi. And again, we'll have the second term will also get cancelled. So we'll have the third term here. So that will be, okay, no, let us not include the error here first. So from this, if we want to find out f dash xi, it is basically of xi plus 1 from h. So this is the formula for the forward, the central difference. If we include the this one, so here it will be h cube by 3 factorial. The first one we take two random points xi and eta. So it will be f triple dash of xi minus f triple dash of eta. So here your error will be, if we divide by h here, your error will be of the order of O of h square. So remember this, in central difference, your order is of the order of O of h square. That is, the error is less here because the forward difference and the backward difference, it had the errors of the order of O of h. That is, it increased directly. As h increases, your error increases. However, O of h square means, since h is very less value here, O of h square, that is h square is less than h here. That is, the error in case of the central difference is much lower compared to the error in case of forward difference and backward difference. That is, your central difference is the most accurate to find the first order difference. So we'll see this by example and MATLAB also. We'll see how the central difference is more accurate. Also, if we try to understand it graphically, we can also see why central difference is most accurate. So if we look into the graphical interpretation, so if we look into the graphical interpretation here, so we have our usual XY plane here, and suppose we have our function like this, and we want to find, say, at this point, the derivative of the function. at xi. Okay. So now, what is the actual, if we forget numerical differentiation, if we are asked to find out what is the slope of this function at that point, what we do is graphically, we draw a tangent at this point, right? That's how we find the actual slope. So what is your actual slope? We draw a tangent here. 1 second. So we draw a tangent to the curve at this point, right? And then we find out the slope of this curve, and that will be the slope of this line at this, that will be the slope of the differentiation of the curve at this particular point. So now what we are doing in forward, backward, and central differences. So this is the line, the slope of this line gives the actual derivative. So now if we take two different points here, say the next point is xi plus 1 and this one is xi minus 1. Okay. Say this is xi minus 1. This is xi plus 1. So what we do here in forward difference is we take between xi and xi plus 1, we draw a straight line, right? We draw a straight line here and we find the slope of this. So this gives me forward difference. And the slope of the line between xi, we draw a straight line between xi and xi minus 1, and that gives me the backward difference formula. Now in central difference, what we do is we draw a straight line between xi minus 1 and xi plus 1, right? So it is something like this. So from here, if you do it perfectly, you can see here this red line and the blue line, both of them represent the forward and the backward difference. And this black dotted line that represents your central difference. And your actual slope is represented by the this green line, that is a tangent at that particular point. So you can see here this black line is almost parallel to your green line. That is, the slope of this line is almost equal to the slope of this green line, that is the actual derivative. Whereas this red line and the blue line, those are not exactly, we can just from seeing, I'm telling, just from inspection, we can see, we can tell that these two are not accurate compared to the black line. That is, central difference is more accurate here. The slope of the red line and the blue line are clearly visible, that these two lines are not parallel to the green line, and hence we can say that it is not equal. Just 1 second. ক্লাস নিচ্ছি একটু পরে করছি ক্লাস নিচ্ছি একটু পরে করছি দাঁড়াও বলছি জাস্ট 1 মিনিট হ্যাঁ বাবা ফোন করছে কখন থেকে তোমার ফোনে বল কি কাজ করছে আমাকে Okay, so here just by inspection from the graphical method, we can conclude here that our central difference scheme is more accurate compared to the forward difference and the backward difference. And also I've given you mathematical proof for that. So then we'll also see that how we can show it by example also how it is more accurate. Okay. So now this was all about the first order derivative. Any confusions or is it clear?
No,
Any
sir,
doubts?
clear.
Okay. So now we see the second order derivative. So in second order derivative, I will not go into much details. Just I'll write the how to derive will show here. So again, here second order derivative means it will involve, if you want to find out the derivative at xi, you will need the values at xi plus 1 and xi plus 2 for forward derivative. For backward derivative, you will need at xi minus 1 and xi minus 2. Similarly, for central difference, you will need at xi plus 1 and xi minus 1. Only 2 points are necessary. So for forward difference, so you can find out f of xi plus 2 will be, if we write it in from this the Taylor series, so f of xi plus 2, it is in terms of f of xi, if we want to write, so it is f of xi plus 2h f dash xi plus 2h whole square by 2 double dash xi. Similarly, f of xi plus 1, if you want to write, it is f of xi plus h f dash xi plus h square by 2. So again, we have these two equations here, 1 and 2, and from this we need to find out f double dash xi. So if you want to find out double dash xi, so here it is 4h square, 2h square, and this is h square by 2, right? So what we do is equation 1 minus 2 into equation 2. If you do, it gives me f of xi plus 2, 2f of xi plus 1 equal to minus f of xi. So this second term will get cancelled. This is 4h square by 2h square minus 2h square minus h square. So this will be h square f double dash xi plus your error will be of the order of O of h cube. From this, if you try to find out f double dash xi, that will be f of xi plus 2 minus 2f of xi plus 1 plus f of xi upon h square plus O of h. So this is the formula of the second order derivative using the forward difference scheme. So similarly, if we use, I'm not again finding out, if we use backward difference, if you want to find out f double dash xi will be given by f of xi minus 2f of xi minus 1 upon h square. So this involves xi, one step backward xi minus 1 and one step further backward xi minus 2. Similarly, from central difference, if you want to find out, it will be f double dash xi will be f of xi plus 1 minus 2f of xi upon h square. So these are the equations. So we can just derive it using the normal. We can write the functions in the form of the Taylor series, and just by some normal simplifications and mathematical manipulations, we can find out our forward difference, backward difference, and central difference formulas. So we'll do one example and then we'll see the MATLAB code for that. So we do one example. First we'll solve it manually and then we'll see in MATLAB also. So suppose your fx is given as minus 0.1, some random polynomial function is there, x cube 0.5 x square minus 0.25x. So this example is only for comparing or finding out which thing is more accurate, which whether the forward difference is more accurate or backward or central difference. Okay. We want to find f dash x at x equal to 0.5 using step size as 0.5 we have given. Okay. So we want to find out f dash 0.5 and h is given as 0.5. So first we use the analytical method and find out what is the true value. Okay. So analytically f dash x we can just differentiate and find out 5x square minus x, and if we substitute f dash 0.5 it is equal to, if we substitute it here this one will get us minus 0.9125. So this is my actual value or the true value. Now we will use numerical differentiation and we will find out using all the approaches. So first we'll be using forward difference. So what does forward difference tell me? Basically gives me f dash xi is equal to f of xi plus 1 minus f of xi upon h, right? So what is my xi and xi plus 1? So your xi is 0.5 here. That is the value at which you want to find the derivative. Xi plus 1 is xi plus h. So xi is 0.5 plus 0.5. It is 1. Right? And for backward difference, we will need anyway. Here only we can find out xi minus 1 is minus 0.5, which is 0. So using forward difference, your f dash of 0.5 equals to f of 1 minus f of 0.5 on 0.5. xi plus 1 is 1 and xi is 0.5. So if you substitute this here, you will basically get if 1 is at 1 the functional value is 0.25 and at 0.5 it is 0.975 upon 0.5, it is minus 1.45. This is the derivative. And what we got the actual value was minus 0.9125 and we are getting using forward difference we are getting minus 1.45. So using step size h equal to 0.5. So we'll also come into whether the step size is introducing any further error, whether we can what is the effect of the step size on the error, that also we'll see here. First, let us fix the step size and let us analyze whether the forward difference is more accurate or backward or central difference. Then next we will take the step size also into account and find out which one is whether there is any effect with the step size also. Okay. So now what is the error here? Error is the true value minus approximate value upon true value. So it is minus 0.975 plus, that is minus of minus 1.45 upon minus, sorry, it is how much is the true value? 0.9125. So this gives me around 58% error here, which is too much. Using the forward difference, my error is, it is giving us 58%. Now we will see backward difference. So f dash of xi so here f dash of 0.5 is f of 0.5 f of 0.5 minus f of 0 xi minus 1 is 0 here upon 0.5. So if we substitute this here, f of 0.5 is f of 0.5 is 0.975 minus f of 0 is 1.25. Again, mod will come here upon 0.5. So this is around 39.7%. And so here you can see this backward difference is better. Although the error is here also is too much, it is better than the forward difference. The error here is lower compared to the forward difference. So now we will see the central difference. Here it is f dash xi is f of xi plus 1 minus f of xi minus 1 upon 2h. So your f dash x 0.5 it is f of 1 minus f of 0 2 into 0.5 is 1. So it is basically minus mod again, not mod, sorry, here. Minus 9.975 minus f of xi minus 1 is how much? 1 second. Ah, it is minus of 1.25 upon, sorry, f of 1 is 0.25, sorry, f of 1 is 0.25 minus f of 0, that is, this is minus 1.25 upon 1 means this is minus 1. So your true value was how much? 0.91 minus 0.9125. Your central difference gives you minus 1. Your backward difference gives you, oh, sorry. So here the backward difference, what is the value here? That gave me minus 0.55. Okay. And if you find out the values here, the error basically here mod is not there. This one gives you an error if you want to find out. That is, here it is. So what is the true value is minus 0.9125 minus of 0.55 upon minus 0.9125. So that gives me error of 39.7%. So here your true value was minus 0.9125 of the derivative. Your forward difference gave you minus 1.45. Your backward difference gave you minus 0.55 and central difference gave you minus 1. So from here only we can understand that central difference gives the most accurate value. And here also if you want to find out the error, so it is minus 0.9125, the true value, minus of minus 1. Just a second. So it is minus 0.9125 minus of minus 1 upon minus 0.9125. So here the error is approximately 8.99 or 9%. So here you can mathematically you can see your central difference is the most accurate one. I hope it is clear to you. Is it clear?
Yes, sir.
Okay. So now we'll see the last topic, which is the effect of the step size. Then we'll go to MATLAB. So how your step size or H value that determines the accuracy. So you all know that for any numerical method, the lower is your step size, the more accurate will be its value. Right. So we'll see here. Suppose we'll take another different function here. X for a random polynomial function we'll take 20x 120. Say we want to find the derivative of this function at x equals to 9. Okay. So this is f of x. So your f dash x is, if we just differentiate, so we find out the true value first. We substitute this, we'll get minus 6.5. Okay. So first let us find out, first let us fix the scheme and then first let us find out for forward difference. Okay. In forward difference, so what we did last time was we fixed the step size and then we changed the scheme from forward to central to backward and we compared their accuracy for the same age. So here now we'll do the just the reverse thing. We'll fix the scheme here, that is forward difference, and then we'll see for different values of h what it is giving me. And then we'll fix it for central difference and then we'll see what is the value it is giving me. So first let us use h equal to 0.1. Okay. So if we find this xi plus 1 minus f of xi. So f of xi plus 1 is, so xi is 9. So xi plus 1 is 9.1 minus f of 9. So if you substitute this, you will get minus 6.1. Similarly, now let us use h equal to, just reduce h by one order, h equal to 0.01. So f dash x, if we find out, it is f of 9.01 minus f of 9 upon 0.01. If we find this, it is minus 6.45. So you can see as we have reduced h, our error has also reduced. Your true value was minus 6.5. For h equal to 0.1, you got as minus 6.1. Whereas for when you reduced h by one order, that is h equal to 0.01, you got your error value as, your derivative value as minus 6.459. So we'll just see one more h equal to 0.001 if you use. So your f dash x is again f of 9.001 of 9. So this will be around minus 6.496. Again, your error has further reduced. I hope it is clear to you. So as the step size increases, or as the, so here basically numerical differentiation, it is very simple. So here there are two factors here. One is the scheme which you are using, forward, backward, or central difference, and the other is the value of the step size which you are using. That basically determines whether your result is accurate or not. So now we will see the MATLAB code for this, and we'll see here whether we are getting the same thing what we did in this mathematical manual calculation. Is the screen visible to you, everyone?
No, sir.
Okay, 1 second. Just a second, it is loading, I think. Is the MATLAB screen visible now?
Yes, sir.
Just a second, it is loading. So here, this is my code. So here I have just used a symbolic variable x here, and then I have defined my function. Then I have taken a particular h value, step size, and this is xd. That is the we have to find the this is the value of x for which we want to find the derivative. Just a second. Someone is trying to join. Okay, so here xd is the value at which we want to find the value of the derivative. Then again here this is xi plus 1. So you can see here xd plus h I have used. Subs is the function, the inbuilt function in MATLAB for substituting. In func, in place of x, we are substituting xd plus h. That is xi plus 1. This one is xi, f of xi, and sorry, let me write in comments clearly. This is f of xi plus 1. This is f of xi, and this one is f of xi minus 1. So forward difference, what is the formula? Fxi plus 1 minus fx by h. Similarly for backward and central difference. And this is the actual value. That is, we are using the diff function to find the actual derivative of the function. So using the diff function, we are finding the actual derivative of the function. And in the next line, that is line 26, we are substituting the value of xd. That is the value at which we want to find the derivative. Then we are finding out this error fdf, error bdf, error cdf. What are the different errors? So now we will see here. I'll just run this code. Just 1 second now. See here you can see for a particular value of h, your error in forward difference is some 4%. Your backward difference error is also around the same thing, 4.7%, whereas the error in CDF, it is very low. It is 9.59 10 to the power minus 4. So you can see here what is happening. Again, if we just change the value of h, I have reduced the h by one value. So you can see the errors have further reduced by one order. Is it clear to you?
Yes, sir.
Any questions? No? Then we'll
No, sir.
close for today. We'll meet again in the next class. Okay?
So
Next
no
Friday
homework
we'll.
for today, to this week.
I'll see. I'll see if I have any homework. I'll upload in the group.
Okay, sir.
Thank you. Thank you so much.
Thank you, sir.